Hello world. Today we're going to be talking about linear systems. This is chapter 5 of Strogatz. Okay? So this is a very short chapter and hopefully you would have learned this in like an ordinary differential equations course. But just in case you didn't, we're going to go over all of it right now. So, when I say linear systems, what we're talking about is we have a system of differential equations. So I'm going to call that x dot is equal to ax, okay? Where in fact now x is considered a vector, okay? So say I give you x1 dot is equal to ax1 plus bx2, and x2 dot is cx1 plus dx2. And this is in fact exactly the system that we're going to be working with right now. So what we care about is that the fact that these differential equations are almost coupled together, okay? So we need information about the behavior of x2 to understand how x1 evolves with time and vice versa, okay? And all of that information about how the coordinates are entangled is contained within this matrix, which is very important, okay? And so to solve this system, okay, and I'm going to write it as x dot is equal to capital AX, where A is a matrix, okay? What we want to look for is essentially we're going to look for eigenvalues of this matrix and then solutions. Of course, eigenvalues satisfy that ax is equal to lambda x, okay? And so if we were to convert this problem into, say, x dot is equal to lambda x, okay, then we know that the solution of this problem is just an exponential of argument lambda, okay? So to simplify this matrix problem, we're going to reduce it to the eigenvalue problem. So we'll start by taking the eigenvalues of A, okay? So if you remember, to find the eigenvalues of a matrix, we simply are going to subtract lambda I and take the determinant, okay? And the reason for this is we're going to have like A lambda is equal to, ax is equal to lambda x, and so we subtract both sides. We get a minus lambda I, where I is the identity matrix, x is equal to 0. And then we look for non-trivial solutions of this equation. And so non-trivial solutions can only occur when this matrix um, is not like linearly independent, okay, or when it's non-singular. And so that occurs when the matrix has a 0 determinant. So we're just going to take the determinant of a minus lambda I and set it equal to 0 to find non-trivial solutions to this equation, okay? So by setting this determinant equal to 0, we are going to see that we have a minus lambda, b, c, d minus lambda. Take the determinant of this matrix here, okay? We're going to get a minus lambda, d minus lambda, minus bc is equal to 0. Now, sorry about that. So we have ad minus a plus d lambda plus lambda squared minus bc is equal to 0. Okay. And so now we can see that we're going to have a characteristic equation that looks like this for lambda. Okay. And notice that this characteristic equation, in fact, has some very important coefficients. So this coefficient a plus d is in fact the trace of the matrix. Okay. So remember, the trace is just the sum of all the diagonal terms of the matrix. So this is just the trace, and I'm going to call it tau for trace. And then this term, the constant coefficient term, is in fact just the determinant of the matrix. Okay, so I'm going to use a little triangle to denote determinant. Wow. Okay, and determinant. Excellent. Okay, so now I have that lambda squared minus tau lambda plus the determinant is equal to 0. Okay, and so applying the quadratic formula, I have that my eigenvalues are precisely tau plus or minus the square root of tau squared minus 4 determinant all over 2. Okay. And now let's look at what these eigenvalues actually correspond to. Okay. So let's go back to our system of differential equations. We have x dot is equal to ax. Okay. So suppose, for instance, that a has an eigenvalue of 3. Okay. So, and let's just say it has eigenvalues of 3 and negative 1, for instance. Okay. So essentially, I claim that the solution to this system is in fact a linear combination of exponentials with exponent lambda. Okay. So the solution is given by some combination e to the lambda 1 t plus c2 x of t is equal to c1 plus c2 to lambda 2t. Okay. And so this is an interesting argument, and in fact, it's very similar to what you've seen for the general solution of a first order ODE, right? The only difference is that these constants are in fact vectors, okay? And the crucial point about the constants is they're not just any old vector, okay? They're in fact a scalar multiple of the eigenvector, okay? So let me just write that out here. And so v1 is a eigenvector for lambda 1. So an eigenvector satisfies that a v1 is equal to lambda 1 v1, okay? And hopefully you've learned how to solve for eigenvectors and eigenvalues in like linear algebra, okay? So I'm not going to review that right now. The point is, why does this solution actually work? Why is it unique, right? And that's a little bit of a complicated question. You have to get into some more theory to prove the uniqueness of the solution. But essentially, I'll say that if a solution did not satisfy that it was a linear combination of these two exponentials, okay, then we would have problems because over time, as you'll see in the phase portraits we're going to draw here, you'd have to have trajectories that intersected themselves, okay? And the problem with that is that the solutions would no longer satisfy uniqueness. Okay, so the reason why these solutions are unique, first of all, they solve the differential equation, and you can verify that by just plugging it in yourself, okay? And when you plug it in, you're going to get that ax is equal to a times c v1 e to the lambda 1 t plus c2 v2 to the lambda 2t, okay? And now we can apply distribution for the matrices here. And so we're going to get c1a v1 e to the lambda 1t, okay, plus c2a v2 e to the lambda 2t. And now we can see that in fact we're going to get, if we look at just these two terms and isolate them, we're going to get lambda 1 v1, okay? By the nature of this, by the nature of the fact that v1 is an eigenvector corresponding to lambda 1, okay? So I'm going to do this with av2, okay? And then I should have the exponentials here, lambda 1t to lambda 2t, okay? And so now we can do is we can then go ahead and look at just x dot, okay? So x dot is precisely c1 v1 lambda 1 e to the lambda 1t plus c2 v2 lambda 2 e to the lambda 2t. And so we can see that in fact this is equal to ax, okay? And so so this solution solves. A lot of times people are like, okay, you gave me something that works. Like, can you tell me why this works, right? And the reason why is because these exponential solutions are dense in the space of solutions for the differential equation, okay? And this differential equation is well posed in that if you give me an initial condition, like say in the phase plane, if you tell me my initial x1 and x2 at time t equals 0, there's a unique way that the system evolves with time. Okay, and so that's called the uniqueness of the solution. And because this differential equation is well posed, i.e., it has unique solutions, then we know that if we do solve for a solution that satisfies the initial data, it has to be the exact solution. Okay, and that's what we've shown here is that for any initial data, okay, for any initial like x1 of 0, x2 of 0, we can go ahead and essentially plug it in to this equation for t equals 0 and solve for the constants c1 and c2. We'll always be able to do this, okay, because these vectors should be linearly independent. Of course, okay, not all the time is it possible, only when the vectors v1 and v2 are linearly independent, of course, all right? And in the cases when they're not linearly independent, this is no longer our solution form, okay, because we don't cover the whole space. But in almost all cases, we're going to have two eigenvectors that are linearly independent. And then if you give me any initial data, I can construct a solution of this form. And using the theory of differential equations, I can prove that since this linear equation ax, okay, this is like as smooth as you could possibly get. This is infinitely smooth, infinitely differentiable. We're going to have a unique solution. And so since I've provided you the solution, we know it's already unique by the theory of differential equations. It's a bit more complicated to show that, but this is not the level of course where we're going to go into that. Then essentially we know that this is indeed the solution of the differential equation. Okay, so to summarize this logic is that the exponentials is a clever way of manipulating the fact that ax, when it has some eigenvalues, satisfies certain properties, and then we can simplify the problem to an eigenvalue problem, similarly to how you would solve like a regular ODE that's linear. And then we just use a linear combination of exponentials of the form v e to the lambda t, okay, where lambda and v are corresponding eigenvalue and eigenvector pairs. And this works so long as all of the eigenvectors are linearly independent. Okay, so this works for almost all cases. There are certain matrices where it doesn't work. Okay, and we could talk a little bit about that, but you may want to just refer to an ordinary differential equations textbook to figure out how to deal with those minor cases. Um, and so let's continue forward with the theory as it relates to chaos. Okay, so the point is that once I know how these linear systems, what the solutions look like, okay, and actually I probably shouldn't have erased all that. That's fine. I can rewrite it. Okay, so once I know what the solutions look like, in fact, if x of t is c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. So what I care about is the graphical solution of these phase spaces, okay? And so it turns out that the graphical solution, if I look at just x versus x dot, okay? Or excuse me, not x and x dot anymore. We just have x1 and x2. Okay, so turns out that there's very interesting properties when we graph the solutions to this differential equation, okay? And so there's many different possibilities. If we have two eigenvalues that are positive, okay, then essentially I'm going to have that, first of all, if I start on any of these eigenvectors, the other constant is 0, okay? So if I let's plot v1 and v2. So let's say this is v1 and here's v2. okay, then if my initial data lies on v1 entirely, then c2 is going to be 0 in that case, okay? And so I'm just going to live on what's called this unstable manifold, okay? Which essentially means that um, as time approaches infinity, negative infinity, I'm going to approach the origin. Okay, so to analyze these graphically, I'm going to look at the eigenvectors, okay, v1 and v2. And I'm going to note that if I care about kind of the phase plane of x1 and x2, remember we have two differential equations. X1 is equal to some linear function f of x1 and x2, and x2 dot is some linear function g of x1 and x2. Okay, and these are linear. So if I started with initial data, let's draw v1 and v2. Say v1 looks like this and v2 looks like this. If I started with initial data that was on the span of v1, okay, then essentially I immediately know that time is going to be 0, so these exponentials are going to go away. And I'm just going to have c1 as like the scalar multiplier of the eigenvector, and c2 is going to go to 0, okay? So this term is going to be neglected entirely. So the evolution of the system along the span of the eigenvectors is entirely determined by basically this exponential, okay, that corresponds to that eigenvector. And so if we started off with the case that say lambda 1 and lambda 2 are positive, okay, and I'm going to be more specific and just write, okay, I'll write it down here. Lambda 1 is greater than lambda 2 is greater than 0. Okay. So I know that along this uh, line spanned by the eigenvector v1, I'm going to have solutions that grow exponentially. Okay. And so my solutions will be, remember that v1 is a vector, but they're going to have some c1 v1, c2, v2, and then they're just going to grow exponentially by this multiplier e to the lambda 1t. And so I'm going to draw that by arrows to kind of, the arrows again are designated in like the direction of flow along this line. And obviously I've drawn many, many arrows so you can really, really see that it's exponentially growing here. Okay. And now, okay, so now let's look at the other eigenvector. So now, if I just have initial data that starts on v2, anywhere on the span of v2, in fact, then c1 is going to be identically 0, and so the solutions will exponentially grow along the span of v2 with respect to time. Okay, and notice that they're exponentially growing in magnitude. Okay, so as long as the coordinate starts on some positive multiple of v1, then that positive multiple will grow exponentially in magnitude. If I start with a negative scalar multiple of my eigenvector, that negative sign is just going to grow exponentially. So these exponential multipliers are only causing growth in the magnitude of our initial data along the span of the eigenvector. Okay. So now that we've drawn what's happening along these lines spanned by the eigenvectors, we can now look at any initial data, arbitrary initial data, and just recognize that its behavior is essentially going to be a linear combination of what's happening um, uh, along each of the eigenvector directions. Okay, so I'm going to have a component that's on this eigenvector, and I'm going to have a component that essentially projects onto the other eigenvector. Okay, so as I can see here, both of these components are going to exponentially grow with time, and so this particle is going to shoot out into space. But we need to figure out how exactly is it going to shoot out, right? Okay, and so to figure that out, we actually need to look at the relative size of lambda 1 and lambda 2. So if lambda 1 is greater than lambda 2, and they're both positive, then essentially it's going to grow much faster in the direction v1, okay? And so it's actually going to, as time increases, it's going to continue growing in both directions, but it's going to eventually become parallel to v1 because the component of v1 is going to become exponentially larger than the component of v2. And so eventually this trajectory will grow parallel to the span of v1. And then similarly, as time goes to negative infinity, okay, so we can also reverse time in these systems. They're fully time reversible. And when time goes to negative infinity, both of these coordinates are going to collapse down exponentially, right? This exponent is just going to become very, very negative. So they're both going to go to 0. But notice that since lambda 1 is greater, this exponent is going to decay much faster, okay? So as we approach the origin, we're going to slam into the lines given by v2. Okay, so it'll actually look something like this. I'm a bad drawer of this, but it'll look something like this. Okay, so I'm going to slam into the line given by v2. And let me expand my brush size here so you can really see what's happening. Okay, and now similarly, on this opposite side, you can kind of fill in the details yourself. It's actually very useful. So if I start with any initial data, if I reverse time to negative infinity, I'm going to slam in to the line spanned by v2. Remember, because this v1 coordinate, okay, is just decaying so much faster because lambda 1 is greater than lambda 2. So I'm going to slam into the line spanned by v2, and then as time approaches positive infinity, I'm going to grow and become parallel with the manifold spanned by v1. Okay, notice how I called these manifolds. So these lines spanned by the eigenvectors, they do have a special name, and they're called stable or unstable manifolds. Okay, and basically they'll always like intersect the fixed point, which is in this case is the origin. Okay, but either the stable manifold will approach the flow will approach the origin as time goes to infinity. The unstable manifold will diverge away from the fixed point as time goes to infinity, which is exactly the same kind of naming convention that we've been using for fixed points. So it kind of follows nicely. So again, this would both of these lines would be considered unstable manifolds because they both diverge away from the fixed point as time approaches infinity. And in fact, for every unstable manifold, they will always converge to the fixed point as time approaches negative infinity. So if you reverse time, this system will become stable. And in fact, this is what we call an unstable node. If I simply change the conditions and I simply say, like, keep the magnitude of lambda 1 greater than the magnitude of lambda 2, but let's just say I make them both negative, okay? So if I make them, and I'll do it in a special color so you can see that it's negative. What's my negative color? Let's just say yellow seems pretty negative to me. Yeah, so yellow seems negative to me right now, so we're going to go with yellow. So if I instead do like lambda 1 is less than lambda 2 is less than 0, okay? We're going to have the same exact phase portrait. It's just a time reversal. Okay, so notice it's actually equivalent to taking the system we just analyzed and doing the change variables in time from t to negative t. Okay, you'll have the same exact equation, and so we can analyze the negative eigenvalue case, distinct negative eigenvalues case, by literally just reversing the time arrows here. Okay, so let me do it with my yellow pen. So I just reverse the time arrows and I have the same exact system. Ugh, that was a gross manifold. Okay, so now you can see that in this case, in the negative case, we have everything kind of collapsing into the origin as time approaches infinity. And so these would be called stable manifolds, okay? And this system is a stable node, okay? So yellow is a stable node. All right, and that's wonderful. So more formally, without the graphical understanding, I'm just going to write stable node This is the case when lambda 1 is less than lambda 2 is less than 0. Okay, so they're both negative and distinct. Okay, so the reason why I wrote one is less than the other is that basically means that they're not equal to each other. Okay, which is important because the only time when we have like a possibility that eigenvectors might not be linearly independent is if the eigenvalues are not distinct. Okay, so if you have an eigenvalue of like a larger multiplicity than 1, if the eigenvalues are distinct, you will always have linearly independent eigenvectors, and so there's nothing to worry about. Okay, and then back to our beautiful red for the unstable node. We have lambda 1 is greater than lambda 2 is greater than 0. Okay. All right. And so now let's move on to the other cases. So there's a few other cases. Let's go back to our formula for what the actual eigenvalues are. Okay, so I'll write this elsewhere. So our formula is that lambda is equal to tau plus or minus the square root of tau squared minus 4 determinant all over 2. Okay. So we can see that so long as this square root is non-zero, we'll have distinct eigenvalues. Okay. And in fact, the cases that we just went over, okay, are cases in which this square root of tau squared minus 4 determinant is real and specifically less than tau. Okay. Because if it's in magnitude, okay? And because if it's less in magnitude than tau, then essentially adding and subtracting it won't actually change the sign of lambda. So lambda will have the same sign in both eigenvalues. So now if I decided to tell you, okay, let's assume that that the magnitude of tau is less than square root of tau squared minus 4 determinant. Okay, then all of a sudden my eigenvalues lambda 1 and lambda 2 are opposite sign. And observe that there's a really simple, there's the only time when this happens, okay, if you look at the actual input of this square root, the only time when lambda 1 and lambda 2 are opposite sign, and this equation holds true, is when this input is greater than tau squared, okay? And so that essentially means that our determinant has to be negative, okay? So when our determinant is negative, these two will have opposite sign. And then similarly, when the determinant is positive, and this thing is real, then we're going to have the stable and unstable nodes that we just went over. Okay, and I'll write this all out more clearly at the end of the lecture. So going into this case, if our determinant is negative, we're going to have two eigenvalues that are distinct and in fact opposite signs. So lambda 1 is less than 0 is less than lambda 2. So let's again figure out what happens with our system. Okay, might be a nice exercise for you to try this yourself, but essentially we're going to have like v1 e to the lambda 1t plus c2 e to v2 e to the lambda 2t. And now I understand why instructors always tell people to do an exercise after class, because it's so much easier than working it out on the board. And it is good to give people exercises, obviously. Okay, so let's look at this system. Okay, so again, the way I analyze this is I'm just going to look at the line spanned by the two vectors. All right, so let's move this down a little bit. So I'm going to look at the line spanned by, let's call this one v2 and this one v1. Okay, all right, interesting. These origins should line up, by the way. Now, let's just say okay, as we've written it here, lambda 1 is negative. Okay, so that means that this exponential, if say we start initial data on this line, okay, we're always going to stay on the line and it's going to be dominated by this exponential. In fact, it's going to decay. Okay, so this manifold is stable and it's going to decay to the origin. However, if we start on the other manifold, if we start on the other line spanned by v2, then we in fact have a multiplier that's unstable. Okay, and so I'm going to shoot off to infinity as time goes to infinity. in this case. Okay. So now our manifolds, this one is a stable manifold, and this one is an unstable manifold. And so they're moving in opposite directions, and this is very, very interesting. Okay. And so take a moment to think about what the trajectories might look like for an arbitrary initial data. Okay. And so to analyze this, we're again going to look at the projection of the initial data onto these lines. Okay, so we can analyze the projection of any initial data onto these eigenvector lines and just view this as essentially having a component. The solution has a component along the line spanned by V1 and a component along the line spanned by V2. Okay. And so as time goes to infinity, the component on the unstable manifold is actually going to exponentially increase, right? As we can just see by looking at the solution, this exponential with respect to time is just going to grow. And then in the other hand, now we have a negative component for the other exponential. So the projection onto this stable manifold is going to decay with time. So what this looks like is essentially something that looks like this, right? So I'm just going to basically approach and collapse onto V2 as time goes to infinity. All right. And then as I reverse time, the exact opposite thing is going to happen. So this term is going to decay. This term is going to exponentially grow. And I'm going to have something that basically collapses onto the span of V1. All right. And so doing this for all of the different quadrants mapped out by the intersection of these two manifolds here, I can immediately see, and the nice thing is I can just look at, and it kind of looks like a saddle, but I can just look at the direction of these arrows and immediately kind of get the sense of how the flow is going to occur. Okay. So if I just kind of think about this as flowing on a plane, I should look at this arrow and kind of see how the flow should go directionally, just intuitively, like down this line and then kind of sliding through to the left here. Okay. And the derivation of like why this actually works is due to the projections onto the manifolds, but it's much better in practice to just memorize, like, okay, if I have a saddle, I can just look at the directions of the manifolds and just automatically see how it's going to flow, right? So hopefully that's clear. If I were to just make it incredibly clear, if I did something like this was my saddle, okay? These are my two manifolds. Then immediately I would know I had something that looked like this, okay? So I could immediately see, okay, this direction is flowing down and then up to this manifold. So that's how I can immediately do it without even thinking twice. All right, so that's our case for the saddles. And so to summarize, we have nodes occur when, and they look something like this. Okay, let me draw this better. Okay, and they occur when this key square root, tau squared minus 4 determinant, is real and less than tau. So essentially this square root is real and determinant is positive. Okay, and then we'll talk about the cases in stable and unstable in a minute, but saddles actually just occur when determinant is negative, okay? And if the determinant is negative, this thing is automatically real, so we don't need to worry about it, okay? So the last case to cover is when the square root here, tau squared minus 4 determinant, becomes complex. And then we actually have complex eigenvalues. So lambda 1, 2 is equal to tau plus or minus the square root of tau squared minus 4 determinant all over 2. Okay, just a quick reminder here, A, B, C, D. This is my matrix A. Remember that tau is just A plus D, so it's just the sum of the diagonal entries, and then the determinant is AD minus BC. So hopefully you've seen this before, but if you haven't, that's okay. Now, when this thing becomes complex, that essentially means that tau squared minus 4 lambda is less than 0. So the entry of this square root becomes negative, and we get complex eigenvalues, okay? And so there's a few distinct cases that are important. Okay, so when I have lambda 1, 2 is basically going to be some complex conjugate alpha plus or minus beta I. Okay, what I'm going to get, as you've seen in like a normal differential equation, is I'm actually going to get a combination of sinusoidal waves. Okay, so this complex part of the exponent is going to cause solutions that oscillate. So we're still going to have a solution form of x of t is c1 v1 e to the lambda 1t. Solution form is the exact same, and it solves the equation for the same reasons. But once you turn this lambda to be entirely complex or entirely imaginary, then you're going to have oscillations, okay? So you're going to have a solution that can be rewritten in the form x of t is some c1 v1. Actually, I should emphasize that these are different constants, so I just put a v cosine of beta t plus b sine of beta t. Okay, and so the idea is that if it's entirely imaginary, okay, then if we start at some initial data, okay, then what's going to happen is the solutions will oscillate in x1 and in x2. Okay, so both coordinates will be essentially linear combinations of sines and cosines, and so x1 is going to oscillate back and forth here, and so is x2, right? And they're going to do so in a nice uniform way because their frequencies will both be governed by the same beta, okay? All right, and now, and what that will look like on the face plane, I should say, if I haven't made it abundantly clear by writing it, is that this will look like a trajectory that is an ellipse in phase space, right? And now if I allow that this alpha is non-zero, so say that I take just an arbitrary two complex conjugates, okay, and I'll remember, going back to our original equation, this corresponds to a trace being non-zero, okay? So if I assume that alpha is non-zero, then what I'm left with is still this linear combination of sines and cosine waves, but I'm going to have, on the outside, I'm going to have an exponential e to the alpha t, okay? So I am going to have an exponential multiplier that's going to either grow or decay with time. So what that's going to correspond to is these oscillations in the phase space are going to they're going to be damped or they're going to grow exponentially, okay? So in the damped case, I'll write alpha less than 0. Damped case, they're going to spiral inward, okay? And that just corresponds to their amplitude, A, being damped, okay? And then if the alpha is greater than 0, okay, then, and I'll emphasize this red curve is alpha equals 0. So if alpha is greater than 0, we're going to have curves that their amplitude exponentially grows with time, okay? And if we reverse time, again, similarly, we're going to get a stable spiral. Now, interestingly enough, I have drawn this a little bit deceptively, okay? Because I've drawn it as though this blue spiral is spiraling in the opposite direction of the yellow. Turns out that can never happen, okay? So the last thing I'll mention about these complex systems that spiral is that to determine the direction of a spiral, so say I have alpha greater than 0, so I'm going to have what we call an unstable spiral, okay? So amplitude growing, the amplitude of the oscillations in phase space grows with time exponentially. To determine if it's a spiral that looks like this, or if instead I have a spiral that is in the opposite direction, something that looks like this. Okay. So how do I determine what direction the spiral is? And the simple answer to that question is you need to plot in, your initial data, or you at least know a point on this spiral, and you just know a point in the phase space in general. And so if you take any point on the phase space, say 1, 0, and you plot it into your system, x1 dot and x2 dot is equal to I'll just write it out. ax1 plus bx2 to cx1 plus dx2. So if you plot this data into your system of equations, you'll get some value of x1 dot and x2 dot. And that's precisely the tangent vector in the phase space. So say I got something that looked like 0, -2. Okay. It's a very, very convenient example, but I would have gotten a vector that pointed this way. So immediately I know that I can see graphically that this red direction is actually the correct one, and the blue direction can never be correct. Okay. All right, so that's the last thing I'll cover, and let's quickly synthesize all this information. I want to iterate that I expect when I'm teaching this material that you've already covered this in a differential equations course, and you've already gone through many, many examples of like how to solve how to solve a phase portrait of, say, just somebody gives you the matrix A with real numbers in it. I'm assuming that you've gone through that before and you've seen the solution, and if you haven't, then you probably need to refer to some courses in differential equations like ODEs, an introductory level of course to differential equations before you proceed, because that information of like how to solve those systems is really important. And we'll go through it a little bit. Just what we're going to be doing is using these linear systems like x dot is equal to ax. We're going to use them to approximate the phase space of a more complicated nonlinear system at a certain fixed point. Okay, and so similarly to a differential equation, how if you want, you can say you have a fixed point, you can Taylor expand about that fixed point, and let's say you have a function that looks like this. You can Taylor expand, say, around this point, and I can get a line or even a parabola based on how many degrees of my Taylor expansion I choose that approximates the function around that point. So we're actually going to be doing this with systems of nonlinear differential equations, where we look at the fixed points of those systems, i.e. x1 dot x2 dot is identically equal to 0, okay? And for those fixed points, we're going to use a Jacobian to approximate the phase. We're going to approximate the behavior of the phase trajectories around the fixed point with exactly a linear system. So it's going to be invaluable to know how to solve these linear systems, and we'll definitely do many examples, but I'm not going to spend time doing them right now because I don't think it's necessary. Okay, so in very short terms, I'm assuming that you know how to do all this stuff. Okay, this should just be a review. Now, okay, so to synthesize all the information we've gone over, we have stable. Okay, we have nodes. Stable and unstable. Okay, so nodes occur when, first of all, tau squared minus 4 determinant, this value is positive, because remember, I'm going to write it up here so you can just see it. The values of our eigenvalues of our matrix A are given by the trace of the matrix plus or minus the square root of trace squared minus 4 determinant over 2. Okay, so here, when I need this input to be real to have a node, so that corresponds to this being greater than 0, and I also need that the determinant is also positive, so that I get that the eigenvalues are the same sign. And now finally, to determine, so this is the nodes case, and then stable specifically occurs when trace is negative, okay, and then unstable occurs when trace is positive. And you can kind of think about the trace. How I think about it is like the trace will almost give you a intuitive sense of the stability, okay? And that's a very, very sketchy way of viewing it. But as long as you have a real um, okay, so as long as we have a real square root, then this is actually a good trick for just memorizing how it works. So when the trace is negative, that's going to correspond to negative terms in my exponential or negative lambda. And so therefore I'm going to have a stable system, right? Stable that approaches the fixed point. Everything's decaying to the fixed point as time goes to infinity. Whereas if the trace is positive, I can expect that the terms in my exponential are also going to be positive. And so I'm going to have a system that's unstable. Now, I could have a positive trace and a negative determinant, as we'll see in a minute, which is still considered an unstable system. So I'm still at least going to have one um, of my exponents of my lambdas that are going to be positive. So in general, this is kind of an interesting way to view it. And it's okay. The thing is, you need more than just a negative trace to have a stable system. You need a negative trace and a positive determinant. But anyways, let's keep moving forward. Don't want to get lost in the nuances here. Okay, so for saddle nodes, this one's a lot nicer. Okay, saddles, and let me just draw you a picture. A saddle, like we went over, is going to look something like this. So we're gonna have opposite directions, and I drew it totally wrong. We're gonna have something that looks like this. Okay, and the only requirement is that my determinant is negative. How nice is that? Okay, so determinant is negative, you have a saddle. Don't even need to worry about the trace. Don't even need to worry about anything. So the negative determinant, you get a saddle no matter what. Okay, and that's just because if the determinant's negative, then this thing will always automatically be real and dominate the trace. So you'll always have um, eigenvalues of opposite sign that are real. So you get a saddle. Okay, and the last thing we covered is we have spirals, which occur when tau squared minus 4 determinant is negative, so I have a complex eigenvalue, okay? And then my stable spirals occur when, again, trace is negative, okay? Because the trace is what's determining that exponential multiplier e to the alpha t, which is outside of our solution, okay? And this exponential multiplier, this alpha here, is entirely given by the trace because this square root is going to be imaginary, okay? So we have stable when the trace is negative and unstable when the trace is positive. Okay? And so I might have drawing of a stable spiral looking like this, right? The stable spiral is going to go straight into the origin. And then finally, we have centers, which essentially occurs when we still have tau squared minus 4 determinant is less than 0, okay? But now we have tau is equal to 0, okay? So when the trace is equal to 0, all of a sudden we lose that exponential multiplier and we just get undamped oscillations. So we just get perfect oscillations in our phase space. And this is actually super important. These centers are really kind of the rare case that's important. It's very rare to have an actual center because it's rare to have a trace that's a 0. But when you do get centers, they actually show up a lot in things like physics or in conservative systems because they actually show up as the local, I want to say like the local mapping of a certain, if you think about them as, how did they put it in calculus 3? As like, I want to say like the height mapping. What is it called? like an elevation map. Yeah, like if you take an elevation map of a function, say a potential function where energy is conserved, then you're going to have local behavior that looks like centers. And so because of that, this can be super useful in physics where we actually have systems that can oscillate in an undamped fashion. So let's condense all, and this is like the key take-home message of the chapter. If you learn anything, just remember this, okay? So we can construct a diagram where essentially we compare the trace of a matrix and the determinant. All right. And if we look, we have, whoa. I immediately drew it wrong. Wow. Okay. Determinant is on the x-axis, trace is here. All right. So I'm going to just draw a parabola, which is tau squared minus 4 determinant. Okay. And now on this map, I can essentially divide it into all the categories we've talked about, okay, into all these different regions. So in this region here, note it with blue. So everywhere where the determinant is negative, I have saddles. Okay, so this is lambda 1 is less than 0, less than lambda 2. So eigenvalues of opposite sign. And now we, in this upper region, this upper quadrant, I'm going to have a positive trace, so I'm going to have an unstable node. Okay, so this is this region here, and I'll try to change colors so it makes it even more clear. Yeah, let's see, unstable node here. Okay, and then down here I'm going to have my stable node. Okay, and I'll denote the unstable with kind of like little x's here. And then inside the parabola, I'm going to start getting imaginary roots. So inside of my parabola, I'm going to have unstable where the trace is positive and unstable spirals in this region. And then stable spirals in this lower region where the trace is positive. Okay, I want this to be stable. Okay. All right, and then directly on this line here, I'm going to have my centers. So you can see the centers are a lot more rare, okay? And so what you can see is that this parabola, and I'll draw it in black again, this parabola essentially divides the determinant trace plane into areas where the eigenvalue is imaginary. So this is the imaginary eigenvalue in this region of the parabola, and then the region divided on the left-hand side by the parabola is the just purely real eigenvalue. Okay, and of course on this side we can have a, I should say not just imaginary but a complex eigenvalue. Okay, so it can have a real part, and obviously it does have a real part in these two larger sections for the spirals. And then in this other section divided out by the parabola on the left, we have the eigenvalues have to be real. All right. And then finally, the last case, and then I guess I should say the trace divides the stability. Okay, when the determinant is positive, we have an unstable region where the trace is positive and stable where the trace is negative. And then the determinant, positive or negative, divides between saddles and spirals and nodes. Finally, the cases which were weird, which I kind of skipped over, are cases when the eigenvalues have multiplicity 2. Okay, so essentially this term becomes 0, and so these borderline cases lie exactly on this parabola, and those cases can be things like star nodes. So star nodes are when you have an eigenvalue of multiplicity 2, but you still have two linearly independent eigenvectors. And so essentially you get something that looks like straight lines approaching the origin in all directions. Okay. And then the other thing you can get is you can get degenerate nodes. which essentially you only have one linearly independent eigenvector, so you only have one line, and then it looks like how Strogatz describes it in the book is essentially it looks like you have a a a halfway point between a spiral and a node, right? So like if I were to just barely extend this further, I might get like a node, for instance, okay? Or if I were to keep twisting it and take away that final manifold, I would just get a spiral. So these are like the borderline degenerate cases, the borderline between the spirals and the nodes, and they're much more rare. They occur when you have eigenvalues of multiplicity 2. If you're interested into how you can plot these phase portraits and the general solution forms, you should look into that in like a differential equations textbook. I'll quickly tell you that if lambda 1 equals lambda 2, and you can either have solutions of the form basically c1 plus c2x, or t, it should be t at this point, t e to the lambda 1t v1. Okay, so this turns into a polynomial of order t, so long as there's only one linearly independent eigenvector, and if there's two linearly independent eigenvectors, it collapses down to the normal form that we already discussed. Okay, and so refer to the textbook on these and kind of do your own research. The important part is that you really know how to work around this diagram, okay? And so you should be very familiar with I give you a matrix. All you need to do is just calculate the determinant and the trace, and then you tell me exactly like where it lives in this diagram. What type of fixed point is it? Is it a saddle? Is it a node? Is it a spiral? What's its stability, right? And saddles are technically considered unstable, okay? Just for information. The last thing that I haven't mentioned, which I should mention for full clarity, is what happens on this vertical axis here, okay? Because that's the only part that I haven't defined yet. And on the vertical axis, we actually have a line of fixed points, okay? Okay, so the determinant is 0. We're going to have that lambda 1 equals lambda 2 is equal to the exact trace of the matrix. And for an interesting reason, if the lambda is exactly the trace of the matrix, we're going to have fixed points, which are essentially a vertical line. So we'll have something that looks like this, where we lose the uniqueness of the fixed point, okay? And what that corresponds to is it requires that the matrix essentially has a row of zeros, okay? And so when the matrix has a row of zeros, then we're essentially saying like, in this instance, well, let me change it to make it match the picture. So in this instance, we have like x1 dot is equal to x2, and then x2 dot is equal to 0. Okay, and I should actually, so it's a 1 0. Okay, so in this case, I'm going to have exponential growth in the x1 direction. So I'm going to have arrows that kind of exponentially grow out, lines that grow out along the x1 axis. But then along the x2 axis, nothing's happening, okay? So if I start at any fixed x2, I'm going to stay there for all time. So I'm always going to live on the horizontal line. And specifically, if I start with x1 equals 0 and x2 is equal to some constant, then I'm going to stay there for all time, which means that I have a line of fixed points, okay? So this is the only time when you can have a line of fixed points is if your determinant is 0, okay? All right, so this was a lot, and I kind of really beat this chapter to the teeth, and it probably would have been much faster for you to just read it. Please make sure you're comfortable with this material. Please make sure you're well versed in understanding how to apply this specific diagram I have written out in front of you to very quickly solve. If I give you a linear system, x dot is equal to ax, you can quickly tell me, okay, what type of phase portrait is it? And you can graph, find the eigenvalues, find the eigenvectors, and totally graph the phase portrait. If you're very comfortable doing that, that is going to be invaluable to us when we move up to higher order systems, because In higher order nonlinear systems, like I said before, we're going to be taking the linear approximation centered at the fixed point, okay? And so when we do that, we need to understand the stability of the phase portrait to understand what kind of fixed point it is, okay? So there's going to be fixed points that locally look like saddles. There's going to be fixed points that locally look like spirals, right? And so that's going to tell us a ton of information we can kind of piece together about the behavior of our system as a whole if we know the local behavior around our fixed points using a linear approximation x dot is equal to ax. Okay, thank you all for listening. I will let you go, enjoy, get ready for chapter 6. We're going to delve into higher dimensional, specifically two-dimensional systems of nonlinear equations. Have a good night.